All right, let's take some time to go through examples for Chapter 4. I'll just jump right in. What elements would you expect to exhibit properties most similar to those of chlorine? Strategy here is to know the fact that elements that are in the same group, these are the up and down columns, will usually have similar properties. So if we find chlorine, we'll see that it's in group 7A, which are the halogens. Other elements that would be similar are fluorine, bromine, and iodine. Those are the other nonmetals in group 7A, and then we should expect those to have somewhat similar properties. But you may be asking yourself, what about astatine? It's also in group 7A. Well, it's not a nonmetal. It's actually classified as a metalloid, so that's why it wasn't included. But for the most part, you can find elements that are in the same group as one another and be pretty safe to say that you should find some similar properties. Let's jump into the second example. Without using a periodic table, give the ground state electron configuration and block designation. Where is it in the periodic table? Does it reside in the S, P, D, or F block of an atom with A, 17 electrons, B, 37 electrons, or C, 22 electrons? Classify each atom as a main group element or transition metal. Strategy here, know the filling order of electron configurations. A good way to remember it, and just to make sure you always do it correctly, is to use this picture at the right that I'm highlighting here. I recommend memorizing this. You only have to write it a few times. You'll have it committed to memory. Remember the order of these. You don't have to write the little boxes around as long as you write the letters and orient them exactly as this picture has it, so that you can draw these arrows as I'm highlighting here, just like this. And it will give you the correct filling order. One other thing you want to know is how many electrons will fit in the S area, P, D, and F. S holds a maximum of 2 in its one orbital, and as it states here, every orbital holds a maximum of 2, but some of these have more than one subshell. When we move to P, there's 3 types of P, which will hold a maximum of 6. You don't see the 3 types like you do in the orbital diagrams. So with the electron configuration, you just give the total. So this is 2p6, 3d10, 4f14, 5f14, and so forth. There's some examples. Let me read through these and assume that we'd be filling all the way to 7p and put in as much electrons as we can go. So this would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. Now, hopefully you don't have to go that far in every one of your situations, which you don't. I'll go ahead and tell you don't. You just go as high as however many electrons you have. Now, there are 3 examples where 17 electrons, 37, and 22. So take a moment, pause it, work them out, and let's check them. Here we go. Part A. 1s2, 2s2, 2p6, 3s2, 3p5. If we add up these numbers, it should equal 17. 2, 4, 10, 12, 17. Where does it reside? Well, it ends in P. It's in a P block area. It's not in the very middle. It's a main group element. All right, let's look at B. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. Ends in S. It's in the S block. Also a main group element. And if we add all of these up, it should add up to 37. And in part C, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, ends in the D block, and that's actually a transition metal. All of those that end in the D area, that transition metal area is the D block. One thing that's closely related to this is orbital diagrams. That's where you draw the boxes. You'll actually show the 3 boxes for P, the 5 boxes for D, and the 7 boxes for F. And just remember that each box holds a maximum of 2 electrons. One other thing that's closely related is assigning the 4 principal quantum numbers, N, L, M with a little subscript of L, and M with a little subscript of S. I'll post either a video myself or give you a link to some nice videos to get some extra practice on those. Some people are asking to be able to have a little bit more tutorial with them. All right, let's keep going with these examples and go to the third one. It says, referring only to a periodic table, arrange the elements phosphorus, sulfur, and oxygen in order of increasing atomic radius. Our strategy here is to know the trends of atomic radius. You probably read in the book that radius, and I'll start with, even it's not listed here, but the easiest one to remember is as you go down, it gets bigger because you're getting new rows of electrons, new energy levels. However, as you go from left to right, it gets smaller. Some people have a hard time remembering that because you're thinking, well, I'm getting more electrons. Why doesn't it get bigger? That's because as you put electrons in that same energy level and you get more and more and more in there, it tends to squeeze down and have what's called an effective nuclear charge that just pulls in towards the center of that nucleus. So remember, in these trends, left to right decreases atomic radii, top to bottom increases. Let's see if we can arrange these three. It would be oxygen, then sulfur, then phosphorus. You could look at a atomic radii chart and make sure that they are in the correct order. Also, the trends aren't perfect, they're just general, so there are some circumstances which the trends will not be sufficient. If you had, for example, to look at the periodic table for bromine and silicon, bromine's radius is 114, where silicon has a radius of 118. You wouldn't know that unless you just had to memorize or had to look at the chart. But in the most part, you could look at the general trend. And of course, if you're asked to look at a trend, hopefully the question would have that trend be illustrated correctly. Our fourth example, would you expect sodium or magnesium to have the greater first ionization energy? Second question, which should have the greater second ionization energy? Ionization energy is the energy required to actually remove one electron from the outermost energy level. The second ionization energy would be to remove the second outermost electron that's present. Our strategy here is to consider the effective nuclear charge and electron configuration to compare ionization energies. One thing that we know off the bat is that sodium has 1 valence electron, it's in the first column. Magnesium has 2 valence electrons in the second column. Our solution is the first ionization energy for magnesium is greater than that of sodium because magnesium's to the right of sodium in the periodic table. As the further you get to the right, higher energy. Magnesium has a greater effective nuclear charge, so it's more difficult to remove that electron. However, if you go to the second ionization energy, sodium's is greater because the second ionization of magnesium removes the valence electron, whereas the second ionization of sodium removes a core electron. It's always going to take more energy to remove a core electron. So let's think about it with some numbers that come from a chart. The first ionization energies of sodium and magnesium are 496 and 738, and the units here are kilojoules for every 1 mole. The second ionization energies of sodium and magnesium are 4,562 for our buddy sodium and 1,451 for magnesium. And those, of course, are in kilojoules per mole as well. For the fifth example, it says for each pair of elements, indicate which one you would expect to have the greater first electron affinity. Electron affinity is the opposite of ionization energy. This is being able to put in electrons. Part A, comparing aluminum and silicon, and part B, silicon to phosphorus. Our strategy here, once again, consider the effective nuclear charge and the electron configuration to compare these. In part A, aluminum is in group 3A, silicon is in group 4A. What that means is aluminum has 3 valence electrons. Here's the electron configuration. We see 3s2, 3p1 for a total of 3 in its outermost shell. Silicon has 4 valence electrons. That is 3s2, 3p2. We have these 2 and 2 is 4 in its outermost energy level. Phosphorus is in group 5A, so it has 5 valence electrons. And then here's an abbreviated electron configuration. Just like the other 2, we find 5 electrons in the outermost energy level. So comparing these, the electron affinity for silicon is greater than aluminum because silicon is to the right of aluminum, therefore has a greater effective nuclear charge. It increases as you go right. If we are comparing silicon to phosphorus, silicon again is higher than phosphorus because although phosphorus is to the right of silicon, adding an electron to a phosphorus atom requires placing it in a partially occupied 3p orbital. The energy cost of pairing electrons outweighs the energy advantage of adding an electron to an atom with a larger effective nuclear charge. It's a mouthful, but basically what it's saying is it's going to take more energy to pair the electrons up rather than just to half fill the orbitals. Kind of goes back to Hund's rule when you're looking at degenerate orbitals that are of the same energy. If we fill, for example, a 3p, we have 3 orbitals, all the same energy. We can fill orbital 1, orbital 2, and orbital 3 with 1 electron, rather than pairing up. When we start to pair up, it does require a lot more energy than just filling them individually, which is how they naturally fill when you go bottom up when you're doing your electron configurations. Let's put a visual with that. Here's aluminum, silicon, and phosphorus. We're just looking at the 3rd energy level. Here's our 3s with 2 electrons in it, and here's our 3p with 1. Here we have silicon with 3s2 and then 3p2. There's our 2 electrons there. And then phosphorus, we have 3s2, 3p3. The first electron affinities of each of these, adding in electrons, are for aluminum is 42.5, silicon is 134, and phosphorus is 72. So again, as we were mentioning on the last slide, when I add in an electron for aluminum, I can put it in either of these places, and it's degenerate energy, meaning the same energy as this electron. When I fill silicon, I can put it in this orbital. And then when I fill for phosphorus, I need to start pairing up. I got to pair up somewhere. Okay. Moving on to the 6th example, for carbon and nitrogen, use their effective nuclear charges and atomic radii to compare the attractive force between the nucleus in each atom and the valence electron that would be removed by the first ionization. Our strategy here is to look at the effective nuclear charge for carbon and nitrogen, which are 3.14 and 3.83. The atomic radii of carbon and nitrogen are 77 picometers and 75. The ionization energy is 1086 kilojoules per mole for carbon, 1402 kilojoules per mole for nitrogen. The charge of the valence electron in both cases would be -1. Our solution for carbon, we have the 3.14 value times -1 divided by the distance, and this is in picometers, 77, and this will be squared. Comes out to be -5.3 times 10 to the -4. For nitrogen, we're going to be using 3.83, -1 once again. Distance is different at 75. We square that. Plug in the math. Hopefully all the math here is correct. -6.8 times 10 to the -4. Note that it doesn't matter what the units we use for the distance between the charges. We're not trying to calculate a particular attractive force, only compare the magnitudes together. So both of these are 10 to the negative 4, so we're just comparing the 5.3 and the 6.8. The negative sign also is going to indicate that the force is attractive rather than repulsive. So positive would be repelling, negative is attractive. So our number here, the calculated number for nitrogen, is about 28% larger than for carbon. So really here you would just be given the values and then plug in the relationships and compare which is larger and smaller. The seventh example, write electron configurations for the following ions of main group elements. So we've already practiced electron configurations before, but they were for neutral examples, and that's when we were given the number of electrons. For these, we're given the charge. How we can figure out our number of electrons is to look for the atomic number. The atomic number always represents the number of protons, which is constant. The electrons are the same if it is neutral. However, if it does have a charge, be it positive or negative, it's a difference in electrons that makes it have a charge. If it is more electrons than protons, it's negative. If it is less electrons than protons, it's positive. So for nitrogen here, with a 3- charge, it will have more electrons than protons. Barium will have less electrons than protons, and beryllium will have less electrons than protons. So again, you can write the electron configurations for the neutral atoms and either add electrons if it's negative or remove electrons if it's positive. So let's take a look at those. The solution for these will have, and they've abbreviated these using the nearest noble gas in brackets. So this is an abbreviated electron configuration. And it's 2s2, 2p6. You'll notice it's also the same as the nearest noble gas, neon. For part B, we have krypton is the nearest before it, 5s2, 4d10, 5p6, which is also the same as xenon. And the last one, just 1s2. Alright, so the next example, write electron configurations for the following ions of D block elements, and these are zinc with a +2 charge, manganese +2, and chromium +3. So our strategy here is to write the electron configurations for the atoms, just like you did with the last one. Then add electrons if it's negatively charged or an anion. Remove electrons if it's positively charged or a cation to account for the charge. The electrons removed from a D block element must come first from the outermost S subshell, not the partially filled D subshell. So one more time. The electrons removed from a D block element must come first from the outermost S subshell, not the partially filled D subshell. So these are abbreviated all from argon. We are getting to 3D10. This takes us to 3D5 for the second one. We're removing from the S. And then the last one is 3D3. Write these out in the complete electron configuration and then convince yourself why these abbreviated configurations match and are the same when you remove it from that nearest S. So as we think about it, be sure to add electrons again when it's negative, remove when it's positive, double check and make sure the electrons are removed from a D block element in the S subshell before coming from the D. Ninth example. Identify the isoelectronic series in the following group of species and arrange them in order from increasing radius, so going from smallest to largest. The ones they have here are potassium cation, neon, argon, krypton, a phosphorus -3, sulfur -2, and chlorine. This would be phosphide, sulfide, and chloride. Strategy. Isoelectronic series are going to be the ones that have identical electron configurations but different nuclear charges. Determine the number of electrons in each species. The radii of isoelectronic series members decrease with increasing nuclear charge. So maybe write that out a couple times to convince yourself of those strategies. The solution for these, the isoelectronic series includes potassium, argon, phosphide, and chloride. They're all 18 electrons each. In order of increasing radius, potassium, then argon, then chloride, sulfide, followed by phosphide. If we think about this, when you have identical electron configurations, the attractive force between the valence electrons and the nucleus will be the strongest for the largest nuclear charge. The larger the nuclear charge, the closer the valence electrons will be pulled and the smaller the radius will be. In general, a cation is going to usually be the smallest. Anions are going to be the largest. So here's our smallest end and our largest end. This also has the neutral, 1 electron versus a 2 electron charge versus a 3 electron charge. So you can see the general trend here. Nice trend. Going from positive, neutral, -1, -2, -3. Smallest, largest. So that ends all of the slides that I wanted to go through for Chapter 4. And I will find some other ones to post up that will go through quantum numbers, and then anything else that you want to see, just let me know either on Friday during our meeting or send me an email, and I'll either make a video myself or put up some more videos. Thank you for watching this, and good luck as you continue to study.